Hello, I'm Jonathan Kress and I'm going to discuss a problem in which we're looking at a function and trying to determine how many real zeros there are for this function. This function is a cubic, but the results we'll find could be found for other polynomials and even other differentiable functions. And I'll just say up the front that the theorems we're going to be using require a continuous and differentiable function. So we'll definitely should mention that, and we'll be using the intermediate value theorem and the mean value theorem. Now the intermediate value theorem will allow us to say that if we have an interval on which the function changes from positive to negative or negative to positive, then there must be a zero in that interval. And a crucial point in this is that the function is continuous. We will then look to see whether we can find intervals that have only a single zero in that interval, and therefore we can then count up the number of single zeros there are. Because the intermediate value theorem doesn't tell you anything about how many zeros there would be. You need to use another argument, and the strategy we'll use will be to look for intervals where the function is increasing or decreasing, strictly increasing or strictly decreasing, and then conclude that there could only be one zero in that interval. And that argument will in a less direct way use the mean value theorem. Okay, so let's make a start. So we have a cubic here, and we probably know roughly that a cubic might have one or three real roots. And we would like to find places where the cubic is positive and where it's negative, and then conclude there must be a zero in between. So let's just quickly draw a cubic. Might look something like one of the following things. If this is 0, I'm not going to draw it accurately or draw all the axes, but it might look something like this, or it might look like this, or it might look like this. Okay, and then it also could look like, could just have no turning points or something like that. Okay, so we've got a number of different possibilities to consider. Now, you can see that in each of these pictures here, well, this one here, it's increasing all the way. This one here, it's increasing and then decreasing and then increasing. And same with these two here. And the place, so this one and this one and this one only had a single root. This one here actually has 3, and you can see that one of those roots occurs between the two stationary points. So perhaps we'll start by finding or seeing if there are stationary points for this cubic to help us to decide on which intervals we're going to use. Okay, so for that we need the derivative. Okay, so p dash of x is 3x squared minus 24x plus 45, and that factors nicely as 3 outside of x minus 3, x minus 5. Okay, you can check that easily. So we can see immediately that there are two stationary points, one when x minus 3 is 0 and one when x minus 5 is 0. So x equals 3 and x equals 5 will give me the stationary points. And so we have actually one of the situations like this with the two stationary points, and we perhaps want to find out whether it's like this or like one of those. So we need to calculate the value of p at these two stationary points. So p of 3 is just substituting 3 into this, so it's 3 cubed minus 12 times 3 squared plus 45 times 3 minus 51, and that is 3, just happens to be also 3, and p of 5 at the other stationary point is 5 cubed minus 12 times 5 squared plus 45 times 5 minus 51, and if you work all that out you find that's minus 1. Okay, so we can see here between 3 and 5 the value of p has changed from positive to negative. So because p is continuous, there must be a 0 in between. Okay, so we can now perhaps actually state that using the intermediate value theorem. So using these two facts here, so p of 3 is 3, p of 5 is -1, and since p is continuous on the interval from 3 to 5, the intermediate value theorem says that there will be a point at which the function p takes any value you choose between 3 and -1, and we're going to be interested in where p takes the value 0. Since p is continuous on the interval from 3 to 5, the intermediate value theorem says there is a point C somewhere in the middle such that P of C equals 0. In other words, there is a 0 somewhere in that interval. Okay. Now, we would like to prove that there is only one 0 in that interval, and so we need to have an argument that shows that. You can see from the derivative here that we should be able to work out whether this function is increasing or decreasing on that interval. So I might just do that now. So if this is a real line, there's 3 and there's 5, and I'm interested really in whether p dashed of x is positive or negative along here. P dashed of x is 3 times x minus 3 times x minus 5. And it'll be positive when we're multiplying positive things together, or if we multiply two negative things, or if, and it'll be negative when one's positive and one's negative. And clearly for negative values over here, these two factors are both negative, and so the product will be positive. So the derivative is positive. In between 3 and 5, 3 will be x minus 3 will be positive and x minus 5 will be negative, so that'll be a positive times a negative, and overall it'll be negative. And over here we're greater than 3 and 5, it's a product of two positive numbers, so it's positive. And so the function p has got a positive slope here, a negative slope here, and a positive slope here. And you can see that this one will be a maximum and a minimum. And in between, most importantly, it's the slope is negative and it's decreasing. Now the fact that the derivative being negative in here means that the function is decreasing relies on the mean value theorem. And the mean value theorem requires the function to be differentiable, which it is. Okay, so since p is differentiable, on the interval from 3 to 5. The fact that its derivative is negative means it's decreasing. And p dashed of x is less than 0 for x in this interval. P is decreasing, and hence there can only be one 0. One 0 on the interval from 3 to 5. And this, as I said, really does use the mean value theorem buried in there. Okay, now of course we've only found one zero, but perhaps there are more. I might now draw a slightly better picture. Here's the point 3, and here's the point 5. And we know that there's a stationary point up here and a stationary point down here where it's negative. So it does something like this. And so that's one stationary point, that's the other. And we've just decided, using the mean value theorem, that because the function is continuous, in this interval here, it must have a 0. And because its derivative is negative, it's decreasing, and there can be only one 0. But looking at this picture that I've drawn, it looks like there's certainly another 0 here and another 0 here. How could you check that? Well, over here, the function is increasing, and over here it's increasing. So if there is a 0, there could only be one. And, well, is there a 0? Well, the function value here is positive. Somewhere down here the function value is negative. And so the intermediate value theorem will tell you that there is exactly one 0. So since p is increasing on this interval from -infinity to 3, there can be at most one 0, and I'll just say similarly for the other interval on the other side. There can be only one 0 on this interval on this side. So we've shown that there can be only one 0 on each of these intervals out here because the p is increasing or decreasing. So let's have a look at an interval over here. And I'll just note that p of -1 million is definitely a negative number. I don't really need to calculate that. It should be pretty clear. And it's positive at this other end here at 3. So p of -1 million is negative and p of 3 is positive. And p is continuous on the interval between these 2 points. So it's continuous on the interval from -1 million to 3. So the intermediate value theorem can be applied, and it tells us that there must be a 0. So and I'll just abbreviate to IVT for intermediate value theorem. The IVT says there is a 0 on this interval from -1 million to 3. And we now just need to consider what happens over this side. And so again, notice that p of 1 million is definitely a positive number. We'll just repeat the same argument. And so that's somewhere way out here. P of 5 is negative. And p is continuous on the interval between those 2 points. Okay, so the intermediate value theorem tells us that there is a 0. So there is a 0 on this interval. So we've concluded that there is a 0 on an interval from here, and there can only be one. There is a 0 on here, there can only be one. There is a 0 here, and there can only be one. In total, that's 3. So we've shown there are exactly 3 zeros. So P has exactly 3 real zeros.